We're going to talk about polynomial functions and their graphs today. First thing we're going to talk about is the end behavior of functions. I have created 4 different graphs for you and 4 different functions. I want to talk about the functions first. This first one is f of x is x squared plus 5x minus 3. This next function below it is f of x is x to the 4th minus 2x cubed minus 2. The next function is f of x is x to the 4th plus 2x cubed minus x squared minus x plus 2. And the last function is f of x equals x to the 6th plus 2x to the 5th minus x cubed minus x minus 2. A couple things to note right away is that when we write functions, we write them in descending order according to the exponents of the variables. So in this first one, I go the second power, the first power, then my constant term. The next one, I go the fourth power, the third power, then my constant term. Here I go 4, 3, 2, 1, then the constant term. Here I go 6, 5, 3, 1, then the constant term. Now polynomials, as we studied earlier in the chapter, means that all my exponents have to be whole numbers. That means they have to be 1, 2, 3, 4, etc. And I'm allowed to have constant terms as well. Now when we talk about the degree of a polynomial, if I write them in descending order, the degree of a polynomial is the highest degree term. So in this case, if I write them in descending order, it's the degree of the first term. So this first polynomial is degree 2. The second polynomial is degree 4. The third polynomial is degree 4. And the fourth polynomial is degree 6. Notice each one of those has an even degree. And that's what we're going to focus on, is whether the degree is even or odd. Now if the degree is even, we look at the graphs, and in this case the end behaviors are the same. They both go up on the ends. In this case, it's up and to the left on the left side and up and to the right on the right side. On this next one, same thing, up and to the left on the left side, up and to the right on the right side on each one of these, okay? And the reason it does it are 2 reasons. The first reason is because it is an even function, okay? The second thing we need to notice about all of these is that the leading coefficient, the number in front of this highest degree term here, is positive. That means all the graphs' endpoints go up on the far left and the far right. Now it doesn't matter that they're all 1. What matters is that they're all positive. If any of these were negative, the ends would both be going down. So we can predict behavior simply based on the degree and the leading coefficient. Okay, now we're going to talk about the behavior of functions with odd degrees. Let's look at each of these functions. Again, I gave you 4 functions, and they're all written in descending order, but on each of these, all I want to focus on is the degree, which is the degree of the first term. I have a degree 3, a degree 5, a degree 5, and in this case, there's no degree written, so it's understood to be degree 1, x to the first. These are all odd functions. Now notice the end behavior on the left. The end behavior on the left, they all go down. Similarly, if we notice the end behavior on the right, they are all going up. Now what 2 things do they have in common again? Well, again, they all have a leading an exponent, a degree, which is odd, and the leading coefficient is all positive. Okay? In this case, it's all 1. We don't care what it is, we care the fact that it's positive. So if I have an odd function with a positive coefficient, it's always going to go down and to the left and up and to the right. Now the only thing that's going to change that is if the leading coefficient is negative. Then the graph basically flips. It'll go up and to the left and down and to the right. So again, we should be able to identify behaviors of functions. We'd be able to look at a graph of a function and automatically tell you, yes, it is an even function or an odd function. Or you should be able to look at the formula of a function and be able to tell how it's going to behave on its extremities as it goes down to the left, as it goes to the far left and to the far right, towards positive infinity and negative infinity. Let's talk about zeros and their multiplicity. We know that zeros are basically where the graph crosses the x-axis. They're the roots of a function. And I give you a function like this: f of x is 1/2 times x plus 2 quantity times 2x minus 3 quantity squared. If I were to multiply this out, this actually would wind up being a cubic function because this is x to the first power out here, and x to the second power will be x squared times x is x cubed. But what I care about is the multiplicity. This is already factored for me, which is really nice. Now, my factors are negative 2 and 3 halves. If I notice, x plus 2, if I solve this for 0, this becomes negative 2. And 2x minus 3, if I solve that for 0, becomes 3 halves. Now, what is a multiplicity? Well, multiplicity, we look at the factor, in this case x plus 2, and that whole x plus 2 is understood to be raised to the first power. So that means that the 0, negative 2 has a multiplicity of 1. This 2x minus 3, this whole thing is raised to the second power. So this multiplicity is understood to be 2. What does it mean to have a multiplicity of 1 or 2? Again, we really aren't going to focus on the 1 or 2, we're going to focus on the odd or even. So when it has an odd multiplicity, what that means is that at that point, the graph passes through the x-axis. In other words, on one side it's going to be negative and the other side is going to be positive. It's going to cross through from negative to positive and hit 0, or it's going to cross through from positive to negative and hit 0. Now, to have an even multiplicity means that the graph goes down, it touches 0, and it comes back up. Or it goes up, touches 0, and goes back down. It never crosses the x-axis, or it never crosses the axis. Let's look at an example of that. In this case, we have f of x equals 1 half times x plus 2 times 2x minus 3 squared. This is the graph. Notice my zeros are at negative 2 and at 3 halves. At negative 2, notice what it does. It crosses the x-axis. It actually goes through it to where it's negative on this side and positive on that side. At 3 halves, it doesn't cross the axis. It goes down, it touches the axis, it makes the 0, and then it goes back up. So understand when I'm talking about multiplicities, I'm talking about how it behaves at the 0. Does it cross it, or does it just go and touch it? Finally, we're going to close on something called the intermediate value theorem. And this is actually a pretty well-known theorem, and it's one of those things, once you figure it out, it makes complete sense. So basically, I'm going to use an example to explain it. I'm going to have basically an interval. In this case, I'm going to use the interval 2 to 3, and I use square brackets to include those endpoints. And I'm going to have a continuous function. That's the key, is the function's continuous. In other words, you're to sketch this function, you can sketch the entire function left to right without ever lifting your pencil, okay? And I'm going to give you the function as x cubed minus 2x minus 5, okay? And what I'm really looking for is I want to plug in these endpoints, 2 and 3. And say if I plug in 2 and it's positive, and 3 and it's negative, well, to go from positive to negative, I have to cross 0 somewhere in between. And vice versa, say I plug in 2 and it's negative, and then 3 and it's positive, then to go from a negative to a positive, I had to cross 0 as well. And that's what we're really looking for. We're looking for a sign change. We're looking for where we go from a negative to positive or positive to negative, because if we do that, that means that function had to be equal to 0 somewhere in between because it was continuous. Remember, I said I could draw it, so if I'm going to draw from a negative y value to a positive y value, I have to cross the x-axis. Or if I'm going to sketch from a positive y value to a negative y value, I have to cross the x-axis. Here's my function, f of x equals x cubed minus 2x minus 5. My interval was 2 to 3, so I'm going to plug in 2. I get 2 cubed minus 2 times 2 minus 5. That's 8 minus 4 minus 5, which is negative 1. So f of 2 is negative 1. I'm below the x-axis. If I plug in 3, f of 3 is 3 cubed minus 2 times 3 minus 5, which is 27 minus 6 minus 5, which is 16, which is above the x-axis. So f of 2 is negative, f of 3 is positive. That means somewhere in between 2 and 3, I had to be equal to 0. So somewhere in that interval, 2 to 3, the function crosses 0, or the function has a root. And that's what the intermediate value theorem is trying to get at.